So today topic is Hemerytrin. So this is one of the important topic in bio-inorganic chemistry. So here we just need to learn the structures of deoxyhemerythrin as well as oxyhemerythrin, deoxy and oxy. So deoxyhemerythrin means here two iron atoms are present in a +2 oxidation state. Both iron atoms are in the +2 oxidation state, and one iron is having a hexa coordinate. So N shows the histidine nitrogen. Here's histidine, and another iron shows only two histidines, and these two irons are connected through the carboxylic group of two amino acids. They are aspartic acid and then glutamic acid. Okay, now here we have a OH. So in the deoxy form, this is the deoxy form. In the deoxy form, the points we should remember is both iron atoms are present in +2 oxidation state, and this OH group acts as a bridging ligands, and this plays a crucial role during oxygen transport. This plays a crucial role during oxygen transport. It acts as a proton donor, and we will see what is the actual mechanism involved during oxygen transfer. And then next point is one iron atom is hexa coordinate, another iron atom is penta coordinate, and here the iron coordination number is 6 +2 6, and here it is 5. So oxygen will binds to the iron which is having a 5 coordination, not to the iron which is having 6 coordination. And another thing, here both the iron atoms are present in a high spin oxidation state, so it will be most likely to be a paramagnetic compound. So this is about the deoxyhemerythrin, and now we'll go for the oxyhemerythrin. So oxygen will come here, iron, both iron atoms here in a +3 oxidation state. Aspartic acid, glutamic acid, and two histidines are here, and here 3 histidines. Now this hydroxy group, I'll explain. Forms a bond through hydrogen bonding. Okay, so here we have O double bond O, right? Now this here it's converting into O minus, and here also O minus. Now this iron is giving 1 electron to the oxygen. That's how it's becoming a +3 oxidation state. And now this hydrogen is going from here to here, and that's where this iron also becoming +3 oxidation state. Okay, when this hydrogen goes here and this oxygen takes 1 electron from this iron, so that's why it's become Fe+3. So in oxy form both the irons are Fe+2 in oxidation state. In deoxy form both the iron atoms are +2 oxidation state. In oxy form both the iron atoms are +3 oxidation state. So we'll see what is the mechanism here involved. So initially we have Fe+3, Fe+2, OH, Fe+2. So this is deoxy form. Okay, now this will get converts into Fe+3, OH, and Fe+2. Okay, so this we called as a So this is called as semi meth form. Okay, so this is unstable. This we call it as intermediate. So this shows mixed valent, one iron atom in plus 3 oxygen state, another iron atom is plus 2 oxygen state, and deoxy form we call as a reduced form. So we have read in cytochromes, when we are talking about cytochromes, there also we come like Fe plus 2 in oxygen state, this is a reduced form. In Fe plus 3 oxygen state, this is oxidized form. So this is in the reduced form. So after proper transfer of oxygen, so it gets converted into oxidized form. In oxidized form, both iron atoms are present in plus 3 oxidation state. So oxidized means this is oxy-form. This also called as oxidized form. So why we are calling it is oxidized form means, so here I have explained that, so both the iron atoms are donating 1 electrons to the oxygen, so because of that we are calling this one as a oxidized form. Okay, so this is the oxidized form. Now there is one more intermediate exist, that is after losing this peroxide, it can also exist like this: Fe plus 3 OH, Fe plus 3, and here it can be L, it can be any ligand. So this is called as a chemistry-Hemerytrin, and this is also oxidized form. Okay, so here two intermediate we have to remember, that is semi-meth-hemerythrin and meth-hemerythrin. In semi-meth-hemerythrin, so one iron atom is in plus 3 oxygen state, another iron atom in plus 2 oxygen state, whereas in meth-hemerythrin form both the iron atoms are in plus 3 oxygen state. So we call it as a oxidized form, and this also oxy-form also we call it as a oxidized form. And another thing, the color of the oxyhemoglobin as well, oxyhemerythrin, so deoxyhemerythrin and oxyhemerythrin. So deoxyhemerythrin is a colorless, but this compound shows red color. Okay, so here oxygen transport is taking place in the form of peroxoform. So here we are getting a peroxo species. So this point we need to remember. So same thing we also read in case of hemocyanin also, but here you remember that in hemerythrin oxygen is carrying like this in the form of peroxo species. And the best way to identify the oxygen binding, whether it's transferring in the form of dioxygen or monooxygen, so if we want to identify in which way it's transferring, the best spectral techniques which we use to identify is Raman spectroscopy, resonance Raman spectroscopy. Okay. So we know that we have 4 species: O2 plus, O2, O2 minus, O2, 2 minus. So we know that O2 plus means this is the oxidized form of oxygen, oxidized form of O2, and this is neutral, this is a reduced form, and this we call this reduced form we call as a superoxide, and we call this one as a peroxide. Okay, and we see the stretching frequency for these oxygens. In case of oxidized form, the stretching frequency comes around 1900, and this is 1500, and this is 1100, and this is 800. So it's very easy to remember. You just need to remember this 1900. If you remember this 1900 minus 400, 1500, 1500 minus 400, 1100. So 1100 minus 300, 800. So this way you can remember it. Okay, and as we know that what is happening here, so when we are increasing the negative charge, when we are doing the reduction, the number of antibonding electrons are increasing. If we see the MOT diagram, the antibonding electrons in antibonding orbitals are increasing. Because of that, bond order is decreasing. Because of that, the stretching frequency also decreasing. And then dioxygen oxygen distance in angstroms. So this also very easy to identify. So as we know that bond order is directly proportional to the inversely proportional to the bond length, right? So here more bond order, that's why it will be less bond length. Here less bond order, that's why more bond length. Okay, so they may ask in examination point of view that by giving oxidized form as well as peroxide form, so which one will be having a more oxygen distance. So more oxygen distance will be there in peroxide form. So when we see for oxy form, so here I hope you can see this. Here we have a two stretching frequency. Here we have, I will write here. So iron, oxygen, this stretching frequency comes around 444 centimeter inverse. Okay, this stretching frequency comes around 844 centimeter inverse. And one more stretching frequency, that is iron, oxygen, this one, iron, oxygen, it shows two stretching frequencies. One is at 486, another one is at 757. So 486 one is symmetric stretching frequency, and 757 is unsymmetric stretching frequency. Okay, if we see this one, the stretching frequency of oxygen is coming around 844, and just now we have discussed that so here the stretching frequency of oxygen is 844 centimeter inverse, and if you see here, it's falling in this range. Okay, right? So 800 means it is 800 means 800 to 1100, right? So it's falling close to 800, that is 840 centimeter inverse. That's why the oxygen in case of hemerythrin carried in the form of peroxide form. Okay, I hope it's clear up to now. And next we are going to talk about the magnetic property of oxyhemoglobin and deoxyhemoglobin. So in oxy form, we have two iron atoms in a +3 oxidation state. Okay, so now +3 means it is a T2G3, so T2 5 electrons are there. So we have two iron atoms, we have 2 5 electrons, so total 10 electrons. So these 10 electrons couples antiferromagnetic coupling, or we can say spin coupling. So because of that, oxy form is diamagnetic. If it gets coupled, we get a 5 pairs like this. So this is the diamagnetic compound. So further we can characterize this compound by using EPR spectroscopy also. You will not get any peak here. So like for deoxy form, you may get the peak because unpaired electrons are there in oxy form. And how we know that hemoglobin shows cooperative binding towards the oxygen. But if we see the hemerythrin, so hemerythrin is not that cooperative like hemoglobin. So it is like 1/4 of hemoglobin. The binding tendency will be the 1/4 of hemoglobin. So but hemoglobin shows cooperative binding oxygen, but hemerythrin 1/4 of hemoglobin cooperative binding it shows. And we know that hemoglobin binds very strongly to the carbon monoxide compared to oxygen. So hemoglobin binding capacity is greater for carbon monoxide compared to the oxygen. Okay, So that we call as a carboxyhemoglobin. So this carboxyhemoglobin means like when vehicles are when CO is gas is releasing from the vehicles, if we take that CO inside our body, then what will happen, we get carboxyhemoglobin will form. So because of that, person may fall down, and if it's more, person may die also. Next, for hemerythrin case, in case of hemerythrin, this is the difference between the hemoglobin and hemerythrin. So oxygen binding capacity is stronger than CO. So this is because of, so we have seen in case of oxyhemoglobin, so what is happening here, so there is a hydrogen bonding between the oxygen and this hydrogen. Okay, so because of this hydrogen bonding, hemerythrin shows selectively binding to the oxygen compared to the carbon monoxide, whereas hemoglobin shows more for carbon monoxide and less for oxygen. And so this hemerythrin we can also characterize by using mass bar spectroscopy. Mass bar spectroscopy. So here we'll get in the mass bar spectroscopy the environment we have to see. So we have two iron atoms. So both the iron atoms are having a close to octahedral form. They are having close to octahedral form, but this is not a perfect octahedral form, but close to octahedral form. So definitely for oxy form we can expect that a doublet, because we have two iron atoms, one is Fe+3, another one is Fe+2, another one is Fe+2, but this 5 coordinated, another one is 6 coordinated. Because of that we can expect the doublet, even okay, if we'll get a doublet. For even oxy form also we'll get a doublet, because as we know, as we have seen in case of oxy form, here oxygen is binding to the only one iron atom, not to the another iron atom. Okay, so because of that these two iron atoms are different. So here also we can expect a doublet for mass in the mass bar spectroscopy. In case of deoxy form also, because one is 5 coordinated, another one is 6 coordinated, there also we can expect a mass bar doublet in the mass bar spectroscopy. So another point I want to say that here only one iron atom is involving in the dioxygen binding, but both the iron atoms are getting oxidized. So this is very important. So this question have been asked many times in examination point of view, that even though only one iron atom is involving in the oxygen binding, but both the iron atoms are getting oxidized. Okay, so this is about the hemerythrin. So till now, if you have any doubts about this hemerythrin, you can write in the comment box. Thank you.